Hi, my name is Nikos Nikolaris, and today in this class I'll talk to you about the design of two commercial processors. Most of you haven't met me before, and I would like to take a minute to introduce myself. I'm working for ARM Research, and in my role in ARM, I'm looking to the memory system for future Cortex-A processors. The reason why I'm here today giving this class is because before I joined ARM, I was a student at Uppsala University. I was one of Eric's PhD students. And back then I was looking into performance analysis for memory systems using simulation and real hardware. In 2010, if I remember correctly, I also took the AVDARK class as a student. And today, I'm really excited and honored to be back in this virtual classroom. In today's class, we will look into some of the latest trends and advances in data center processors. We'll take as an example two popular high-performance processors, and we will look into some of their design decisions. I'm not planning to give you a full overview of their specs and features, because I don't think that's very interesting. Instead, I'd like to focus on a few of those features and designs and see what is their impact on performance, energy and cost. Before I move on very quickly, I have to point out that the views expressed in this talk are by no means endorsed by my employer, and all the material I will present today is based on publicly available information. And with that, let's move on to the more interesting stuff. Many of us use many cloud services in our everyday life, whether we realize it or not. For example, take your smartphone. Many of the applications on your smartphone rely on a cloud service. And to meet this demand for cloud applications and services, companies like Google, Facebook, and Amazon build more data centers. What this means for processor vendors is that this is a great opportunity to increase their sales, sell more processors. This is the reason why more processor companies focus their development efforts on data center processors. Traditionally, Intel dominated the data center, but in recent years, AMD, Cavium, Qualcomm and others tried to challenge this. The data center processor design aims at two things. First, improving performance. And performance is determined mostly by two metrics in the data center. The first one is throughput. For throughput, think for example the rate at which Google can service incoming search requests. And the second one is tail latency. Think that while Google needs to make sure that it can service a high number of requests on average, it also has to make sure that none of them should take way too long. At the same time, the processors for the data centers have to keep low costs. And the main factor that are associated with the cost of with this cost is purchasing the processor and the cost for running these services. That would be the electricity bill for running these processors. With these design goals in mind, we're going to have a look at two high-end processors that target the data center. The first one is Intel Xeon processor, which is codenamed Skylake-SP. And the second one is a new processor by Qualcomm, the Centriq processor. We'll split our analysis into two parts. We'll have a look into the design of the processor core, and once we've done that, we'll see how all those cores are put together to form a system. In the next section, we'll start by looking more closely at the microarchitecture of the processor core. You have already seen some basic core designs. In previous lectures, Eric walked you through the evolution of the core design through the years. You started off with the concept of a pipeline that splits instructions in smaller steps. Pipeline processors can run at higher frequency as their smaller stages can fit in smaller cycles. Then you saw some optimizations in the pipeline that improve ILP, such as the superscalar pipeline and the outer order pipeline. He also studied the Thomas-Schüll algorithm that lays out basic principles for instruction scheduling in an out-of-order pipeline. Modern core designs also aim at improving ILP, and while there has been a lot of innovation, the basic principles remain the same. Keep these principles in mind. They will help us understand more modern core designs. Now, this is a high-level block diagram of the Intel Xeon processor. As you can see, essentially the core is made up of tiles that repeat. These tiles contain the basic building block of the processor, and within that we find the core. For now, we'll focus on the design of the core, which in this picture is shown in a green box. If we zoom in further inside the Skylake-SP core, we find functionality that is outlined in this block diagram. You can already find that many of the components in this diagram are similar to the components of your familiar out-of-order pipeline. At the top, we have the front end of the processor, and at the bottom, we have the back end. You will remember that execution in the front end follows the program order, while in the back end, execution can be out of order. For example, the Tomasulo algorithm can determine in what order instructions execute in the back end. Let's start with the front end and see how instructions flow through the pipeline. Instructions are first fetched from the 32 kilobyte instruction cache. Then they are decoded and cracked into simpler instructions that we call microops. The microops get renamed, and then they enter the reorder buffer. Instructions that have been decoded before, for example instructions that execute repeatedly inside small loops, are cached in the microopt cache to avoid having to decode them again and again. So instructions that we have decoded before and cracked into microops, they'll be stored in this microopt cache, and once we execute them again, we can index in this cache, get the microops right away. In the back end, when we have those microops, they will be directed to the right port to execute depending on their type. For example, integer microops will be directed to one of the LUs through the ports 0, 1, 5, or 6. Or if it's a load instruction, it will go to the load store unit through ports 2 or 3. Those memory instructions will then query a 32 kilobyte level 1D cache, and if the data is not found in the level 1D cache, then they will also query a 1 megabyte level 2 unified cache. Now let's move on to the Qualcomm Centriq processor. This is a high-level block diagram of how the Centriq processor is organized. As you can see again, essentially the Qualcomm processor is also made up of tiles that repeat. We'll now have a look at the design of what Qualcomm calls the Falkor Duplex, which in this picture is shown with these blue rectangles. There are 24 duplexes, and each one of them contains 2 Falkor ARMv8 cores. The 2 cores in the duplex share a 512 kilobyte level 2 unified cache. This is the block diagram of the Falkor core. Once again, at the top we have the front end of the processor, and at the bottom we have the back end. And again, instructions execute in program order in the front end, and they can be the microops in the back end, they can execute out of order. In the front end, the instructions are fetched from the instruction caches, and the Falkor core has actually 2 of them. There is a large 64 kilobyte level 1 instruction cache, but there is also a smaller 24 kilobyte level 0 instruction cache. This extra L0 cache allows instruction fetches in a single cycle, and in most workloads the vast majority of instruction fetches should be L0 hits. But to make the L0 fast, it has to be kept small, and this is the reason why the Falkor has a bigger level 1 instruction cache that can fit much larger working sets. Once an instruction is fetched, it will go into the instruction queue and the expand stage, which decodes the instruction and cracks it into microops. But according to Qualcomm, as most ARM instructions are fairly simple, they are cracked into a single microbe. Now, there is no traditional reorder buffer, and the combination of some of the reservation stations and the renaming logic will maintain the order of the instructions until they retire. Then the microbes enter the backend. Microbes will be forwarded to the write port and pipe depending on their type. You will notice that not all pipes have the same number of stages. Qualcomm stresses the fact that the pipeline stages in the backend differ for different types of microbes. There's a small number of stages for integer instructions that will go to pipe Y or Z, and only a single stage for branches that will go to pipe B. But more complex microbes, like vector microbes, will go to the pipes Vx and Vy, which feature many more stages. And as you've seen previously in the basic pipeline processors, the reason why we do that is we want to break complex operations in multiple stages so that we can run the processor at higher frequency, but we also want to free up resources as quickly as possible, and therefore simple instructions will go through fewer steps. Finally, in this design, there's a 32 kilobyte data cache for memory accesses. So this is just an overview of some of the basic features in the Falkor core. Many of the details that we haven't covered, some of which are not even publicly disclosed, are quite important for Intel Qualcomm. It's after all small differences that determine which core performs better at the end of the day. But what I would like you to take away from these slides is that the basic principles of a modern out-of-order pipeline should already be familiar from previous classes of this course. The processor core is very important for performance and energy. But there is another component which is just as important, and this is the memory system. The memory system has to deliver the data to the core on time without big delays. Especially these data center processors with tens of cores need a highly optimized memory system to reach their peak performance. The cores are connected together with a coherent interconnect, and through that to the main memory and the I/O devices. In the next section, we will look into the interconnect of these two processors. Both of them are very sensitive to throughput, and therefore they need a high number of cores. The number of cores is determined by the performance of the interconnect. The Intel Xeon processor has up to 28 cores, and Qualcomm Centriq processor has up to 48 cores, organized of course in those 24 duplexes. You have studied memory systems extensively in previous classes. You have seen cache-coherent shared memory systems, and you saw two different ways to implement cache coherence. The first one was directory-based coherence, where we have a directory that tells us where the data currently lives, and snoop-based coherence, that we basically snoop the caches, all possible caches, to find out where the data is. And both systems have different pros and cons. Then you studied the basic architectures of interconnects. You first saw a basic bus, and then systems with a crossbar interconnect. And with all that knowledge in mind, let's see how modern processors' memory systems are organized. Let's start with the Intel Xeon processor. This is the block level diagram of the system in an Intel Xeon processor. At the top row, we see a number of I/O devices, such as PCIe links for connections to peripheral devices, and UPI, which is to connect Intel Xeon processors together. So this is used only in multiprocessor configurations. The chip has also two DDR4 memory controllers. Each of them has 3 channels, and then we have 28 nodes connected in a mesh network, and each of these nodes has a core. Now, this is the first generation of the Intel Xeon that uses a mesh network. Previous generations Xeons, Intel used a ring interconnect. The ring interconnect is relatively simple to implement, and for the 22 cores of the previous generation Xeon, it was efficient. This time, Intel wanted to increase the core count without increasing the memory latency, and this is the reason why it chose the mesh network. As you can see in the block diagram, the mesh network is essentially like a two-dimensional array with 36 nodes. 28 of these nodes contain a core and a slice of the LLC and a slice of the snooze filter. This means that the LLC and the snooze filter are distributed. Any node in the mesh network is connected with its 4 neighbors, with connections up, down, left and right. The latency of any memory request is determined by the location of the source and the destination. In this diagram, for example, if a core needs to access a memory location that's in the LLC slice of a neighboring core, the request has to go only as far as one node away. But if the data is in the cache of a core further away, then the request has to travel longer. So the latency of any memory request can actually vary depending on where the source and the destination are, how many hops away they are. Now let's move on to Qualcomm Centriq, the Qualcomm Centriq processor. Now let's have a look at how the processors and the I/O components and the memory controllers are connected together in the Centriq processor. The interconnect in the Centriq processor is a bidirectional ring bus. As we said before, the ring bus is a relatively low complexity interconnect which allows for lower development costs and fabrication costs. But at the same time, the higher the number of nodes in the interconnect, the higher the maximum latency a request can experience. This is ultimately one of the limiting factors for the number of cores that the system can support. But having the concept of a duplex, and with 48 cores in total, Qualcomm offers one of the highest core count processors at the moment. So with that, we're getting at the end of this lecture. So in this lecture, we went through some of the basic design choices of two popular but vastly different processors. And we saw the requirements to optimize performance and reduce the total cost of ownership that these processors had to meet. We first saw the microarchitecture of the Skylake-SP and then the Falkor core, and then we went through the design of the pipeline and their memory system. I hope that this class has shown you some of the basic trade-offs and motivated some of the design choices in these two processors. And with that, I would like to thank you all for your attention and conclude this talk.